Here we go. And I'm gonna have to share my screen from the tablet. Okay, so this is okay. So this is what we had covered so far. So remember what we have done. We started with investigation of a system. Can the system be modeled from first principles? If we say yes, the question is the model linear? And if the model was linear, we were on this path over here, okay? This line. If we could not model it from first principles, the approach basically is to assume a certain model and try to fit the model to the data. Okay, so again, there was a question here, can we safely experiment with the system? Okay, so let's go slightly on this side.
Bu first principle dediğimiz fiziğin kuralları falan filan değil mi?
Yes, that's what it is. So from first principles means, do you really have an understanding of the system? Do you know how it works? Do you understand the physics and chemistry of it, is what we mean, okay? So can you write some equations from the start? So if we can experiment with this system, okay, we can ask, can we assume a linear model? If we have a linear model, or we can assume a linear model, we actually go to this. You see this line is coming from a linear model presumption here. And this goes to the question of, do we really know system parameters? Often the answer is no. But theoretically, for example, in 302, we were assuming that we knew all the system parameters. Okay? So if the system is linear or can be assumed to be linear, and we know the system parameters, we really go into the domain of 302, where we have all the linear tools of designing controllers. And I'm going to cover this part in a minute. Okay? But let's remember what we talked about the last time. If you don't know all the system parameters, you need to go into a process called system identification. Okay, that means you apply certain test signals to the system, you observe the output, and from this output, depending on what kind of test input you apply, you actually try to estimate the system parameters. Okay, you can apply a step function, you can apply a frequency sweep, which will give you basically an approximate frequency response of the system. Or you can use random signals. We are not going to cover that, but in the stochastic processes area, you know that if you supply, for example, a uniform white noise to the system, you will, at the output, you will observe the power spectral density, which is related with the frequency response of this system. Okay, so from this process, depending on what kind of test input you have, you will determine an approximate transfer function. And if the error with respect to the actual system response, okay, if you apply the same input to the model and to the process, and you observe both outputs, and there is acceptable error in between the both responses, you basically have an approximate system model. Okay. If not, you can change the assumed order of the linear system. You can often increase the order and repeat this process until you kind of get an acceptable error. Okay. So, sorry, I was actually using my mouse on my computer screen, but that's not the screen that is shared. So, sorry about that. Okay. So we are here, right? So in this case, we have an approximate frequency response. So if you want to really work on the frequency response domain, which we have learned in 302, we can actually use gain and phase margin concepts to assess relative stability. And we can therefore design compensators, so-called compensators, in order to improve the stability of the system. That's one way of designing a valid controller. Because in many instances, having a robust, stable system that's going to follow the reference input is the primary purpose of designing a controller. So these so-called compensators are one way of doing that in the frequency domain. Okay. Now, let's see. So over here, right, we are in the 302 domain with a linear system with known system parameters. I guess if you don't want to design a frequency response based controller, what you will do is you will basically join, this other line over here. Okay. So we will take it from there. Okay. That means you have a linear system, but you want to pursue some other approach, assuming that you have an approximate transfer function as well. Okay. So let's take a look at what we can do, or what we know we can do from 302. The first thing that we attempted in 302 was to design a P controller, a so-called proportional controller. Okay. A proportional controller, remember, is where you have a single controller gain K, and you have a whole bunch of techniques like root locus, Nyquist, or route Horowitz, where these techniques gives you the ability to determine what kind of range you can actually use for the gain in order to obtain a certain type of transient behavior with certain parameters like rise time, settling time, maximum overshoot, right? Or you can attempt to have a stability criteria, a robust stability. So, for example, in root Horowitz, you can basically determine what's going to be the range of the controller gain for stable system operation. Okay. Obviously, root locus gives you a much better idea because you know where the closed loop poles move as you change the controller gain K. Okay, so that gives you a better understanding of the transient performance. Okay, let's say you used one of these techniques. The next question that you ask is whether the transient, let me zoom in here, whether the transient performance is okay. Okay, so are you satisfied with the transient performance of the system? Okay, if you're not, we need to follow other approaches. But if yes, the next thing to check is basically whether the steady state error is fine. Steady state error acceptable. Is another check. Obviously, if the answer to that is yes as well, you have a valid controller in this case. Okay, that kind of completes the design. If that's not the case, what do we do? You guys tell me.
Increase the gain?
Well, yes, you can play around with the gain. So maybe let me branch that. In fact, I didn't have this branch, but since you mentioned that, let's say tune gain, okay, increase might be one way of dealing with that. What is the other way of dealing with that? Sorry, who's talking? I guess you will have to randomly arbitrate your access to the channel, right? Is there any one of you who is taking computer networks course? Anyone associated with the computer option somehow? Anyway, in you guys are all using Ethernet, right? Ethernet is what we use in order to access the internet. Okay, Ethernet is a network protocol. In that protocol, there is the computers try to access a common medium, and there might be if two computers tries to access the medium at the same time, that's called a collision. And what is being done in that protocol is that both computers step back, wait for a random amount of time, and retry to access the medium. Because they are using random timers, one of them will access the medium, and the computers also have the ability to detect whether there is a transmission in the medium. So that if you wait a random time and retry, but somebody else is transmitting, so you wait for another amount of time until that transmission is over in order to access the medium again. Okay? This, sorry?
Kibarlık algoritması oluşuyor.
Kibarlık algoritması, aynen öyle. So that algorithm is the basis of Ethernet protocol. It's, I believe, called at least it is called something medium access with collision detect. Okay, so I don't remember the exact name, but this is basically the protocol, and it has its origins in the first attempts to communicate via wireless radio between Hawaiian islands. That is why one of the kind of pioneers of the Ethernet protocol is called the Aloha protocol. Okay, so these are the beginnings of the computer network protocols. Okay, so that's what we experience here, right? We have a common channel. If two persons talk at the same time, the information is garbled. So we need to take turns in accessing the medium. And one way to do that is to, two persons spoke and then nobody spoke because you guys were trying to see who will speak first, right? Anyway, let's come back to our topic here. So what is the option here?
I was saying adding an integrator.
Yes, so we can try so in this case, not only a single integrator, but we might resort to having a PI controller, right? So an integrator basically will take the steady state error to 0 as we have seen before. Okay, so in that case, these two will most likely give us another valid controller design. Okay. Any questions so far? So let's see what happens if we are not satisfied with the transient performance. Sorry. Let's take it from here. So what are your options here? Well, I'm not happy with my line. Maybe I'm going to erase the whole thing. Okay, so again, one way of dealing with it is basically an output feedback approach. In fact, we still have an output feedback because we already have attempted a P-type controller. So that means we are continuing with the output feedback approach. And let's see what we can do, what else we can do in a sense. Okay, so let's ask again, can we safely experiment with the system? Safely experiment with system. That's again a criteria because that's going to determine what kind of approach we will take. Okay. If not, again, we have a dead end here. Okay. But if we can experiment with the system, we can basically, oops, sorry. What I had in mind is two approaches. One is closed loop experimental PID design. This is basically known as, has a name. It is called the Ziegler-Nichols method. Again, we will cover this in our course. So I'm going to put EE407 here. We can also have a different way of doing it. It's called the optimal or optimization based PID design. We will not too much dive into this because it really requires knowledge of optimization. Maybe in 306, the next term, we will have a short introduction to this. But the basic idea is that you have a system with unknown parameters, which are the controller parameters in this case. And you put this system in closed loop in a scenario where with different parameters you obtain different responses. And each time you compare the obtained response with the desired response, and you calculate an error in between. And the optimization algorithm tries to play around with the parameters of the model. When I say model, I mean the controller in the model, so that the error between this designed system's response, actually the error between the desired and the actual response approaches zero. And this optimization-based algorithms do this in an iterative way. That means they change the parameter, retry, change the parameter, retry. But this is not a random experimentation. The optimization theory gives you a means to mathematically, in a mathematically solid way, do this. Okay? So that is called an optimization theory, and we have a grad course as well on optimization. Okay. All right. So what is the other option that we have? Well, we know that we can have much better performance. In fact, any desired performance if we go with a state feedback approach. Okay. So let me see whether I have enough space over here. Yes. Okay. So what is the basis of the state feedback approach? Let's see how much space we have over here. Okay. So we need to attempt a state space formulation. Oh, that's too big. Do you guys have any questions, by the way? Okay, state space formulation. How we can do this? Well, if you already have a transfer function, you know that you can use one of the canonical forms in order to design your state space model. Okay. Let's explore these options. So we can select controllable canonical form. What's the advantage of the controllable canonical form? Why do we choose controllable canonical form? What's the requirement in order to be able to design a controller if you have a system modeled in state space? That was a question. Did you guys catch the question? What is a requirement, a prerequisite that you need to have if you have a state space model and you want to design a controller, a state feedback controller?
Transient performance is not okay.
Well, that's the branch that we are. So we are not satisfied with the transient performance. So we made a decision to use a state feedback, and we obtained a state space formulation, and we want to design a state feedback controller. We know that we have a method called pole placement, right? So pole placement algorithm allows us to locate the poles arbitrarily in the state in the S domain, in the S plane. But there is a catch. The system needs to have a property in order to be able to solve that problem. Do you remember what that was?
Bir öneride bulunabilir miyim?
Kim konuşuyor?
Ömer Faruk.
Buyurun.
Herhangi bir state'i diğer state'lerin ve input'ların aracılığıyla herhangi bir noktadan origin'e getirebiliyorsak controllable diyorduk sana.
Okay. So what you are saying is correct. Is the fact that basically we need to have the selected state space representation to be controllable. In fact, completely controllable in order to be able to design a state feedback controller. Okay, and controllability was related with whether or not you can use the inputs in order to take the system from any arbitrary state into the origin by applying in a finite amount of time, by applying appropriate inputs to the system. Okay, so controllability tells you whether you can do it, and pole placement tells you how you can find those inputs, which means design a controller, right? Because that's going to be the controller that will supply the inputs to the system. Okay? So, what is the property of the controllable canonical form? It is always controllable. So, if you go from a transfer function to the controllable canonical form, you automatically obtain a completely controllable state space representation. Okay? What is the alternative to that? It is an observable canonical form. In fact, not an, but the, right? Because there is a unique observable canonical form. Now, observable canonical form is by itself automatically observable. What is the property of observability? Well, remember that in order to apply state feedback, you basically need the states. Okay? If the states are available, you can design a feedback from the states by multiplying them with certain constants. Okay? But what if all the states are not available at the output? Okay, this is often the case. You have, let's say, 5 states, but a single output. So the states are buried in the system. They are not directly measurable. Okay? If they are not measurable, normally you cannot perform state feedback. What is the alternative? The alternative is that you can design a system called an observer, which will monitor the input and output of the system. And this observer system, which was the final topics of EE302, okay? So all of these are EE302, is that you can design an observer so that the observer eventually will estimate the states so that you can use them as part of a state feedback controller, okay? So if the system is in controllable canonical form and it's controllable, you have to ask yourself whether the states are measurable. The same issue, right? Do I have access to the states? If not, you need to check whether this controllable canonical representation is also observable. So you need to have both a controllable and an observable representation in order to have access to the states somehow. Okay? If the states are not observable, then you cannot design an observer, and therefore this is your grave here. Okay? No option to design a controller in this case. Okay? And if the answer is yes, in this case you will design an observer for this system. Design an observer. Okay? And also here, if you selected an observable canonical form, you need to ask yourself whether the system is still controllable or not. Okay? Chosen representation controllable. If it's controllable, you come to the same location. Okay? If so, this is our yes. And if the answer is no, then you need to really go back to a controllable canonical representation, because since our aim is to design a controller, controllability is a must-have in both cases. Okay? So let's continue. So you design an observer. So what's going to be next? Next will be you will select closed loop pole locations. To satisfy transient performance criteria. And also we can come here with a different location. Here we said states are measurable. No. If the states are measurable, then even without designing a observer, you can directly go here. Okay? You only need an observer if you don't have access to the states, but you need to estimate them from the output and the input of the system. Okay? So what do we do after selecting closed loop pole locations? Well, the only thing that remains is to use pole placement algorithm to determine state feedback gains. Feedback gain vector. Okay, and that completes your design here. Okay, so we have a valid controller in this case. All right. So I have something that was left incomplete here. Sorry, I don't know what happened. Let me share my screen again.
Hocam bir şey sorabilir miyim?
Tabii ki.
State'ler measurable'sa nasıl observable olabiliyor? Yok, measurable değilse nasıl observable oluyor?
Şimdi measurable olmak demek şu demek. Doğrudan ölçebiliyor musun? Observable olmak demek ise input ve output'a bakarak zaman içinde estimate edebiliyor musun demek. Eğer EE302'nin son konularına bakarsanız observer konusuna orada şunu hatırlayacaksınız. Bir sistemin state'lerini doğrudan ölçemesek bile, yani o variable'lara doğrudan access'imiz olmasa bile öyle bir sistem tasarlayabiliriz ki o sistemin state'leri, ki onlar computer'ın içinde bizim elimizde olan bir modelin state'leri oluyor. O state'ler sistemin state'lerine zaman içinde converge ettirilebilirler. Dolayısıyla elimizdeki o modelin ki buna observer diyoruz, observer state'lerini okuduğumuz zaman sistemin state'lerini, estimate'lerini okumuş oluyoruz. Anlatabiliyor muyum?
Anladım hocam, teşekkürler.
Yani bu sonuçta şey gibi düşünebilirsiniz. Çok basit bir örnek verelim. Mesela bir motorunuz var. Motorunuzun hızını ölçebiliyorsunuz ama şaftının pozisyonunu ölçemiyorsunuz. Hızı ölçüyorsunuz ama şaftın pozisyonunu ölçemiyorsunuz. Elinizde bir sensör var, sadece hız ölçüyor. Ama siz pozisyonu bulmak istiyorsunuz. Ne yapacaksınız? O zaman yaptığınız hız ölçümleriyle aradan geçen zamanı kullanarak pozisyonu kestirebilirsiniz. Bu bir çeşit basit bir observer olmuş oluyor. Yani sensörünüz doğrudan pozisyonu okuyamıyor ama hızı okuyor. Siz hızı kullanarak pozisyonu buluyorsunuz bir hesap yaparak. Yani bunun çok daha advanced bir versiyonu olmuş oluyor observer dediğimiz şey. Okay? Let me try to complete this diagram here. We had, is the model linear? No. Now, our approach here will be a question like, is or can a or an equilibrium point be defined? Or operating points be defined? Okay? If the answer to this is yes, you will basically find a linear approximation, and let's call this linearize the model around the equilibrium operating point. Okay? And that gives us a linear approximation and will basically take us to over here, right, where we started. Okay, the linear branch. Okay, obviously with remembering that this linear model is not valid everywhere, but only in the close vicinity of the operating point. If you get farther away from the operating point with a nonlinear system, your model will deviate from what's happening with the actual system, and therefore anything that you design based on that model will basically suffer. Okay? If okay, so here actually apparently I did this way. Let me just rewrite this. Can an equilibrium point be found? So in my diagram, I have separated the equilibrium point from the kind of operating point. So can a nominal operating point be defined? But it's, you might argue whether we really need this as a separate item. If the answer is no, we don't have anything to do, or at least we cannot do anything. If the answer is yes, we basically go here. Okay, same part. Okay, so that's more or less everything that I have. Something like this. And maybe we missed certain things, but these are the things in my mind, and that's, I think, is a good summary. Now, I want to break here and have our small exercise before finishing for today. Before that, do you guys have one or two questions?
Hocam şu non-linear sistemleri linearize edip bir model oluşturuyoruz ya belli noktalar için.
Yes.
O pointler dışına çıkınca da çalışmıyor diyoruz. Öyle olduğunda muhtemel şunları kullan falan diye böyle bir sistem kurabiliyor muyuz yani? Oradan çıkarsa, çalışmıyorsa şunları kullan falan gibi.
Yani birincisi çalışmıyor diyemeyiz. Siz o noktadan uzaklaştıkça performans giderek düşecektir ve stabiliteyi de kaybedebiliriz. Yani dolayısıyla çalışmıyor kelimesi on-off bir şey değil. O noktadan uzaklaştıkça bozulan bir performanstan bahsedebiliriz. Controller'ın feedback sebebiyle disturbance rejection özellikleri bir miktar bunu kompanse etmeye çalışabilir. Ama nihayetinde ideal performansı alamayacağımız, baştan hesapladığımız transient değerleri elde edemeyeceğimiz söylenebilir. Ama çalışmıyor gibi sadece on-off bir yargıda bulunamayız. Bunun dışında tabii ki yapılabilecek şeyler var. Tamamen nonlinear controller'lar mümkün. Ama nonlinear controller'lar bizim şu andaki konularımızın dışında. Yani 404 dersi ve devamındaki graduate seviyedeki 555 Stability Theory of Dynamic Systems dersi nonlinear sistemlerin nasıl analiz edilebileceği, burada konumuz olan equilibrium point bulmayla başlayıp başka stabilitelerinin nasıl analiz edilebileceği, nasıl kontrolörler tasarlanabileceği ile ilgili burada değinemeyeceğimiz başka yöntemlerden bahsedecek. Dolayısıyla o tarafta bir takım şeyler var ama lineer domainde olan tool'lardan çok daha az miktarda orada imkan var. Yani matematiksel tool'lar çok daha sınırlı. Tamam. Evet, şeye geçelim arkadaşlar. Ben kaydımızı durduruyorum.